Hi everyone, my name is Oleg Kroshko, and today I'm excited to share my project, which is dynamic quantization of LLMs via reinforcement learning, or DynaQuant. So this project tackles a key challenge for large language models. They're powerful but extremely resources intensive. So quantization, which is reducing the numerical precision of model parameters, can help bring memory usage and improve inference speed. But one size-fits-all approach is can hurt actually performance. So our goal is to find mixed precision strategy that picks just the right quantization level for each layer. So quantization is already common in model compression. For instance, using 8 or 4-bit weights is widely spread. However, different layers of an LLM don't always respond equally well to precision loss. Some can be heavily quantized with minimal accuracy drop, while others are more sensitive. So we propose using reinforcement learning approach that dynamically decides how to quantize each layer during fine-tuning. Essentially, our agent learns per layer quantization policy, like picking between quantization types such as NF4, FP4, int8, FP16, etc., that balances accuracy and memory usage. So what is our reinforcement learning setup? So as a state, agent observes features like current layer index, weight statistics, like mean, standard deviation, gradient norms, and exponential moving averages of past rewards. So as an action, the agent chooses which quantization type to apply to the current layer from those types that I mentioned before. How our reward is constructed. So after quantizing a layer, we do a short round of fine-tuning to recover from the precision loss. We then measure perplexity and other metrics comparing the quantized model to a reinforced to the episodic reference model. So reward blends four components, which is perplexity difference through the sigmoid to stay in a nice range, and then chiral divergence, penalizing light distribution shifts, attention entropy. So we want to encourage the quantized model to maintain attention diversity, and then main component, which is memory savings. So every time we quantize a new layer, we do the same fine-tuning step for both the quantized model and the reference model. And that way we can accurately compare performance and capture the dynamics. So we tested this approach on GPT-2. We used libraries like Bitsandbytes and our custom implementation for quantization. We use proximal policy optimization, PPO, for the reinforcement learning algorithm. Fine-tuning tasks dataset like Common Sense QA, and for evaluation we use datasets like BullQ and PIQA. So our multi-objective reward tries to ensure that at each step we push the model towards layer that can handle lower precision while preserving accuracy where it's needed. So what are the results? So we have a table in the poster that comparing uniform quantization like FP16 and F4 against DynaQuant. So we observed actually quite significant drop in perplexity, for instance, 15% compared to the baseline, while also saving memory. We also observed boosting accuracy marginally, but still significant, which indicates that the RL-driven mixed strategy can be actually quite performant. So training dynamics plots show that RL rewards steadily improves over episodes, and the validation loss for the quantized model remains close to the reference model. So one interesting heat map that on the poster shows how over multiple episodes the agent tends to pick specific quantization types more frequently than for certain layers. That suggests that policy learns layer preferences. That would, having said that, that would depend on reward weights heavily. So, what are our observations and trade-offs? So, for reward tuning, the reward function is multi-objective. So, if we put more weight on the memory savings, we will get obviously more aggressive compression. If we put more weight on performance, then agent will try to boost performance, but then the problem could be that we will get ourselves into the regions where reward starts to oscillate and is not stable or experience some drops. So the kind of picking up weights is important and a crucial component in this work. So validation stability, because we do short fine-tuning steps after each layer is quantized, we maintain good overall performance. Computational costs. So this approach is quite heavy on compute. However, it could be worthwhile in scenarios where memory or speed balanced with performance is important. So conclusion and future work. In summary, DynaQuant demonstrates how a reinforcement learning agent can learn dynamic per layer quantization scheme to balance accuracy and memory usage compared to uniform quantization. So, and it achieves lower perplexity, higher accuracy, and a reasonable memory savings. Looking ahead, there are several interesting directions that we are pursuing at the moment and plan to in future. So one of them is scaling it up to larger, more capable models. And then another option is trying different reward weights kind of more systematically and metrics. So extending the action space to the agent so that the agent can choose not to quantize certain layers, and exploring curriculum learning or kind of more efficient fine-tuning strategies. Thank you for watching this video. If you have any questions, feel free to reach me. Thank you. Bye.